Hey there, Calc 3 folks, back here to do another video. This was, I kind of promised this along the way when we were looking at those problems involving the change of variable. Those transformations of multiple integration from the rectangular system into either the polar system or that transformation of that being the double integral case, or the transformation in the triple integration, where we were changing from the rectangular system to the cylindrical and spherical coordinate systems. We encountered what we call the Jacobian multiplier in that transformation, in that case for the change of variables. And I said, just trust me, this is what we multiply by within the integrand, and I really didn't give much support for that, and I always promised I'd come back and put together hopefully somewhat of an explanation video to begin at least justifying that change of variable. So that's what I'm here to do today. I did put together this, hopefully it's a brief set of notes as I present them to you, but it does kind of go off a little bit of the beaten path. We are going to look at some linear algebra skills, and we are going to rely somewhat on some matrix algebra that you may be carrying with you from your college algebra days. And I'm also going to probably introduce you to some beginnings of linear algebra here to help justify this change of variables in this Jacobian multiplier along the way. So bear with me here in these ideas. Again, this is a bit of an optional section for you folks at this point. You're out there, you have your test. None of the questions have really much to do with this other than applying that Jacobian multiplier in your calculations. So your accountability is somewhat minimal for you folks out there in the current semester. What we do start with here is we take note in linear algebra, the linear transformation of location, right, in one description of space into a location in another description of space with similar size dimensions can be summarized using what we call a linear transformation matrix, right? That linear transformation matrix is going to be formed using the relationships between the locations found in each of these descriptions of space, where if we're talking about being in n-dimensional space, this linear transformation matrix is going to be an n by n square matrix, where each component in this n by n square matrix correlates to the change in the locations among these spaces. All right, so now this is just my introductory statement, folks. There's it's kind of looking at the big picture here. We're going to kind of drill down into some of these ideas. To begin with, we might generically set this up here with a discussion in n dimensions. Right? We might begin by assuming that we have this n by 1 matrix known as X, illustrating what we would say are locations in our X space, our n-dimensional X space, right? And we might suppose Y is a similarly dimensioned matrix with n by 1 dimensions, right? Illustrating location in Y space, right? Where Y is also an n-dimensional space, right? Such that when we think about matrix X, it takes on this format. It starts at x1, followed by x2, all the way up to x sub n, and these collection of x values indicate location in X space. And Y, matrix Y, this Y space is this location, right, illustrated by these values y1, y2, all the way up through y sub n to account for this n-dimensional Y space. All right. So to begin with, we're just going to make this assumption about X and Y, where what we're going to set up is a transformation from X into these values of Y. We're going to transform perhaps this location at X1, X2, X3 up through X sub n into this location at Y1, Y2 up through Y sub n. right? We're going to make this one-to-one, in a sense, mapping of values in this space to values in that space through what we call a linear transformation of the space described in X to the space described in Y, right? Now the way this is going to happen is with that, what we had set up above, this n by n transformation matrix, this n by n linear transformation matrix, right? If this is our assumptions, then there exists this n by n linear transformation matrix, we call it T bar, or matrix T, such that when matrix T is multiplied in a matrix product with matrix X, it equals matrix Y. And similarly, there exists what we would think of as being what's called the inverse of matrix T, right? That's T with this superscript -1 times matrix Y. That would be equal to what we would think of as being matrix X in our understanding, right? Where what's unique about this matrix T and its inverse is it does produce this, what we think of as an n by n identity matrix when they are multiplied by each other, right? To begin with, this understanding of inverse matrices, right, and this understanding of matrix algebra is a bit of this matrix multiplication here should be familiar to you from your college algebra days, all right? Where what we're using now these matrices to illustrate is this location in n-dimensional space. And where what we are using here is this process of matrix multiplication with this transformation matrix and our description of location in one of those spaces to produce these descriptions of location in the other space. All right? So what we have is this setup, where we can go on to say, furthermore, if R defines this region of what we call X space, right, defines a region of space in X space, and P is a corresponding region that we find, a corresponding region of space that we find in our Y space, the amount of space defined by P and Y will be a scalar multiple of the amount of space defined by R and X, where the scalar multiple, right, is going to be given by what we think of as the determinant of this transformation matrix, right? In a sense, this may be how we're defining location in X and Y, but if we think about having a region of space defined here in X by points, right, illustrated as we see here, right, and we transform it into a corresponding region of space in Y, right, with points describing location in that space as seen here, right, using this n by n transformation matrix, then what we can say is that the area of space described here is just going to be, well, I should back up, and this goes actually either way, but we're setting it up in this understanding. The area of space defined here by this region that corresponds to this region back here in this space will be a scalar multiple of this description of space. In one dimension, this description of space might be length, whereas in 2 dimensions, this description of space might be area, and where in 3 dimensions, it might be considered volume. Beyond volume, we get into the understanding of hypervolume and such, right? Well, here we're going to stay within the 2-dimensional and 3-dimensional understanding, right? But this is the generic understanding with respect to what is going to be happening here, folks. All right? We might now consider this setup, right, specific to 2-dimensional space, right? So here in this setup, we have the ideas presented above in a convention that's a little bit more practical to what we're going to see in our conversion between the two-dimensional rectangular system and points within it to that two-dimensional polar region, right? Where here we might suppose x comma y, which is contained in two-dimensional space, right, and defined by these coordinates x1 comma y1, right, is transformed into this location in two-dimensional space defined by the coordinate m comma n, where x1 y1 gets transformed into m1 comma n1 in this two-dimensional transformation, right? Well, what's then going to exist is a 2 by 2 linear transformation matrix, right? Such that that 2 by 2 transformational matrix given by matrix T, when it's multiplied by x1 comma y1, or when it's multiplied by this matrix location x1 y1, it produces the location m1 n1. Right? If we note here, letting, right, T bar, for instance, be the 2 by 2 transformation just illustrated in general by the matrix given here by the A, B, C, D to describe the 2 rows and 2 columns of this matrix. Then when we take T bar times x1, y1, which equals m1 comma n1, right, it ends up implying that we have T times this equal to this, or that if we think about m1 and n1 in value, and if you recall your matrix products, the way we form the values m1 and n1 with this product is it is this first row times this column x1, y1, where it's a times x1 and b times y1, with those two products added together to form m1. And n1, this value seen here as the, in the second row, first column of the resulting matrix m1, n1, is found by taking this second row of T and multiplying it by this column matrix x1, y1, with C times x1 added to D times y1. So n1 becomes C times x1 plus D times y1, right? Where what we should notice is that this description of m and n in two-dimensional space is really just being described, right, by a set of parametric equations for the parameters of x and y that we see back in two-dimensional space. In this x and y transformation, or I should say in this two-dimensional transformation, this linear transformation of x and y, right, into m and n, that transformation can be represented simply by this set of parametric equations where values of m and n are dependent upon the values of x and y, right? In this this linear relationship, right? M is equal to ax plus by, and n might be thought of as being equal to cx plus dy, right? Now, furthermore, if we take note, if the transformation of xy into mn is described by the set of parametric equations given by this parameterization, right, then the linear transformation matrix, right, which is given by, right, we might point out which is given by T bar equal to this, A, B, C, and D, is such that is equal to the values of what we would think of as these values here. The value of A in T comes from the derivative of m with respect to x. That would be the, I should probably correct these, and I will correct these after the fact. I don't have time to correct all of them now. We should note those are del's, I might have time to correct all of them right now while you folks get caught up on the notes. All right. So this would be the partial of m with respect to x and the partial of m with respect to y for a and b, and the partial of n with respect to x and the partial of n with respect to y for c and d, respectively. Right? These values of a, b, c, and d that make up the transformation matrix from m into n, right? That describe this relationship seen here in the parameterization between values of x and y and m and n, right? Is nothing more than the first partials of the values of m and n with respect to the values of x and y, right? Taking these 4 locations in the matrix for T bar, right? For matrix T. So that is, one thing we will note is happening there in the background of a linear transformation that's happening in 2-dimensional space, is that description of the transformation matrix is describing these partials in this parameterization, right? And then lastly, note, if R is defined as a set of coordinates, right, of x and y in 2-dimensional space, is being transformed into a region of space P, right? In the region, is transformed in the region. Lastly, note if, we should really say here, region R is transformed into the region of space P, there, that sounds a little better, where P is defined by these set of coordinates. What we see then is that, okay, let me go back over that. Okay, so sorry, I was interrupted there. If region R, right, defined in this 2-dimensional space by the coordinates x, y, is transformed into the region of space P, which is given by a set of m and n coordinates also in 2 dimensions, then the area of P will just be a scalar multiple of R's area. As noted, that was what we had said in general up here, right? If R defines a region of space in X and P defines a region of space in Y, the amount of space defined in P or by P will just be a scalar multiple of the amount of space defined by R. Where what is that scalar multiple? It is going to be the determinant of T. Right? Where, again, here we note where that scalar multiple is certainly going to be just given by the determinant of T here. Where if T is this matrix A, B, C, and D, right, the determinant of that 2 by 2 square matrix is just the quantity A times D minus the quantity B times C. Right? It is just this quantity given here. Right? This difference of the product of A with D and B with C. Right? What we will see is that if R has a particular area, right, then P will just be this number times R's area. And that will describe the area of region P, right? The area of P will just be a scalar multiple of R's area, where that scalar multiple is going to be given by this quantity known as the determinant of T. All right? Let's look at a bit more of a specific case. In the specific case, I do return to our generic understanding here. Right? So I consider the linear transformation of what we're going to define to be region R, right, in 2-dimensional space with matrix, I should say with vertices defined by the following matrix X bar, right? Suppose region R is a region of space where this defines the vertices of region R, and we're going to transform this into a region we're going to call region P in space, right? With vertices defined by Y bar, right? We're with vertices defined by y bar, where y bar is going to come from taking some linear transformation of x bar's vertices, right? Or region R's vertices, right? If we think of a pictorial description, let me bring this up. This is probably a little... Here, what I should probably do, let me bring this copy up this way. If we think about what we are setting up here, let's say it here. Well, let's just drop it in right here. Here we go. Right? What we are describing is a transformation for x bar. X bar is going to be these vertices 0, 0, 1, 0, 1, 1, and 0, 1. Right, sorry again, I'm back. I'm jumping back and forth between students and Collaborate and recording this video. So I'm back here. We were again looking at, we have this region of R in two-dimensional space, where we're going to use these four vertices to help us define this region R, where I do have that illustration of R down here. In our two-dimensional space, we're going to have these vertices at 0, 0, 1, 0, 1, 1, and 0, 1. Those are going to define, right, the four vertices for the polygon that defines region R. And in this case, it's defining a square shape for that polygon. And what we're going to do is a linear transformation on all of the points in this region R to produce this region here in two-dimensional space that's going to be defined as region P, right? We're going to perform a linear transformation on all the points in R to make all the points in P, where the boundaries here at 0, 0, 1, 0, 1, 1, and 0, 1 defining R will also have their corresponding boundaries in P, right? Where we're going to just highlight how these boundaries are changing, right, to help us understand how R is changing into P in this case, right? So this is kind of just walking us through the matrix algebra that would be occurring in one of these transformations. And we're using just four fundamental points in our region R, but we would consider this happening at all values within R to produce all the infinite points in P, right? So what we would note then is certainly if R is being represented by these 4 points, 0, 0, 1, 0, 1, 1, and 0, 1, each represented in a column of values, right? Because remember, a location is hinted by a column vector up here, right? And we transform those over into a region of P that's defined by some column vector, right? Using this 2 by 2 transformation matrix, where we're going to get Y from is just taking T times X in this calculation, right? Where we would note T times X in this matrix product, right? We'll take this 2 by 2 and multiply it by this 2 by 4. The result will be itself a 2 by 4, right? We're defined these locations at 0, 0, 2, 0, 3, 2, and 1, 2. We take the first row of T and multiply it by each of the columns, right, making up X. That's going to produce the first row in Y for each of those results. 2 times 0 plus 1 times 0 is just 0, which is this 0 right here in the first row, first column. 2 times 1 and 1 plus 1 times 0 is just 2. That's the value of 2 seen here in this first row, second column. 2 times this one and 1 times this one, right? We'll add it together, right? 2 times 1 plus 1 times 1 is 3, and that's what goes in here. All right. If we continue that pattern, we will get 2 times 0 plus 1 times 1 gives us this 1. Or if we do that now with the second row of t, 0, 2 times 0, 0 produces 0. 0, 2 times 1, 0 produces 0. But 0, 2 times this 1, 1 produces 2. All right? That is, again, that matrix multiplication, that what we call row-column multiplication of matrices. And what that does produce is what we call y, right? This description of y, right? These points in y, right? Where y is describing the vertices of region P. And go back and note those vertices, right? 0, 0 is this vertice right there. So that vertice in X does not change its location at all. As it gets transformed by this matrice, it stays at the exact same location, 0, 0. But when we translate this location 1, 0, right here, this transformation matrix given by T takes its location and moves it to where we would say is the location. Oh, I ought to be careful here. 2, 0. Hold on, I have my matrices back here. I have my illustration backwards. Let me fix this real quick. So I'm back, folks, here. I fixed the image here to match or align with my nodes. Again, what we are transforming is region R into P, right? 0, 0, right? That coordinate on X, defining one of these vertices in region R, does transform into this coordinate 0, 0, or in a sense, this transformation matrix does not change its location. But this location 1, 0, represented right here as this vertice on R, when you apply this matrix transformation, that does become the coordinate 2, 0. That becomes this coordinate here. In a sense, this vertice on R becomes this vertice on P. And every point along that line between 0, 0 and 1, 0 gets translated to some coordinate or some location between 0, 0 and 2, 0 in value. In a sense, these infinite locations get mapped out to these infinite locations. All right? We then note we have that coordinate at 1, 1 on R, right? Defining this vertice on R, where that gets mapped through this linear transformation to this coordinate 3, 2. That would be this location way out here on P, right? In a sense, that location gets mapped out to this location here, right? And again, every point between this location at 1, 0 and this location at 1, 1 on the boundary of R also gets mapped out from this transformation. It's going to get mapped out. All those infinite points found on this boundary will likely get mapped out to all of these infinite points found along this boundary. And then lastly, we see this location at 0, 1, defining this boundary on R, will map out to the location 1, 2, this location on P, right? Where this boundary will map to this boundary on top of, bounding the top of the parallelogram for P. And this side boundary here falling along the y-axis for R will map to this, oblique edge of this parallelogram for P, right? And not only will all these edges map out to each other as we might suspect, but every single point, infinite point making up R, will map to some infinite point, one of the infinite number of points making up the value of P, right? We're only looking at a few points represented by these vertices mapping to these vertices in that transformation, but we could use any infinite number of points in this this matrix for x, and that matrix for x can be any 2 by n dimension that we want, or really we should maybe say it's 2 by m, because it doesn't necessarily rely on the dimensions of the space. What relies on the dimensions of the space is how many rows we have. The number of columns is just the number of points we're using to represent one space being mapped into another. Right? So I'm going to have to bring this down below. So let me go ahead and copy that. Right? And again, I note that illustration down here again, where I want to fix that. Where we go on a little further now and note, well, from our understanding of linear transformations of R into P here, shrink this down just a little bit so we can say this whole idea together here. The area of P here in this two-dimensional space should be a scalar multiple of this region of R here in two-dimensional space, right? Where the scalar factor, right, would be just given by the determinant T, where we can go back and note in this case that determinant of T was just 4 in value. So P, region P's area should be 4 times the area we see here for R. Now, if we take note, the area for R is 1 unit by 1 unit squared, so that is 1 square unit in area. Whereas for a parallelogram, which P, you take note, is parallelogram in its behavior, right? We do have these two parallel sides of equal, of congruent size, right? Two opposite parallel sides of congruent size forms this parallelogram P, right? Where the area of a parallelogram is also the area of the length of the base times the vertical height, right? In this case, the length of the base is 2 units. The vertical height, not the oblique length, but the vertical height is also 2 units in size. So this parallelogram is 2 by 2, or what we would say is 4 units squared. And what we note is P is 4 times bigger than R, where 4 corresponds to the determinant of that linear transformation matrix. All right? So again here, what we're just doing is putting into practice and illustrating some of these initial notes up above here, right? Where we might be talking about this region defined by X being transformed into this region defined by Y, where both X and Y exist in the same dimensions of space, and doing that transformation with a linear transformation, right, would produce, right, a description of that space, the amount of space, with this property, right, being the scalar multiple of one versus the other, right? Where if we do set that up in 2 dimensions, we have this set up here for both our descriptions of the points and for that transformation matrix. Where now if we note in this situation, we're just illustrating what the 2 ideas above in the very specific case of some square region of R transforming into some parallelogram region given by P, right? This region of R transforming into this region of P, right? With the above ideas in play, right? And we do see those above ideas being shown to be true in this very specific example. Right? Where now, we also take note here that in this case, the relationship between x1 and x2 contained in R and y2 comma y1 contained in P can actually be described by a set of parametric equations. All right. In this case, the set of parametric equations would be given by this here, where y1 in P would be described by 2 times x1 plus x2, and y2 in P would be described by simply 2 times x2. Where we would then take note is if we took the partial, and again back to, got to correct that notation there. I'm going to need to note we need partials in that idea. Where if we take the partial of y1 with respect to x1, that will play the role of 2 here. The partial of y1 with respect to x2 is what gives us the 1. The partial of y2 with respect to x1 is what gives us the 0. And the partial of y2 with respect to x2 is what gives us this value of 2 here in our transformation matrix. Right? If y1 and y2 are related to x1 and x2 between these two regions of space, using this parametric relationship, then the linear transformation matrix, right, given by t bar, would be made up of just these first partials, which would be true. All right? Now we go, I think, Jacobian with it all. So let's now consider the Jacobian multiplier in a polar transformation. Now, in a polar transformation, right, we consider the transformation of r comma theta, which describes location in two-dimensional space, into x comma y, which describes location also in two-dimensional space. I know this feels a little backwards in the transformation. When we relate to the integration, we're often thinking of converting a rectangular description into a polar. But here in this idea of this Jacobian multiplier and what we've established above, we do want to set it up with r comma theta being transformed into x comma y. And how I know that is because we're going to rely on this parameterization in our transformation. X and y are going to be thought of as being what? Parameterizations in terms of r and theta. All right? We're going to have a set of parametric equations where the values of x and y depend upon the parameters of r and theta. All right? So the transformation we're going to consider occurring in the above way, right? From r comma theta into x comma y, where in that description of the transformation, we do want to think of the parameterization between x and y and r and theta having this relationship. Where one thing you will note is that is not quite what we have established up here for linear transformations. This is not quite what we see going on here, right? We don't see our result, right, which is going to be x and y, written as these linear functions of r and theta. Instead, what we see is our values of x and y written as these, what? Well, I should say here these polar relationships with r and theta. Where in theory, we're not going to be looking at very, very large regions in our transformation. The way we're going to apply this idea is on very small regions, right? Regions whose size is actually going to head to 0. They're going to become infinitesimally small, right? Where if we do consider this happening over very small regions, it can be approached within the linear context, right? The transformation that happens linearly would be very similar to and become a good approximate of the transformation that's happening here in the polar context. So we're able to use a linear transformation to begin summarizing the polar transformation. All right? We're over very small regions of R, so 2 over two-dimensional space, T bar, right, matrix, the transformation T, can be multiplied by the description of position given by R and theta, right? That 2 by 1 description to produce x comma y, that 2 by 1 description of position, right? Also in two-dimensional space, such that what would be that transformation matrix? Well, it would be given by the partials of x with respect to r and with respect to theta, and it would be given by the partials of y with respect to r and with respect to theta. Now again, you can see here I've messed up that notation, so I got to come back in and fix that real quick. Where if we think about what is the partial of x with respect to r, well, that's just cosine theta, right? If we think about what's the partial of x with respect to theta, well, that's just negative r sine theta. And if we consider the partial of y with respect to r, that's just going to be sine theta. And if we consider the partial of y with respect to theta, that's just going to be r cosine theta. And if this is going to become our description of T bar, that transformation matrix, then the determinant of that transformation matrix is just going to be the quantity cosine theta times r cosine theta, which is r cosine squared theta, minus sine theta times negative r sine theta, which is minus negative r sine squared theta. Now minus the negative makes that again back to positive. And in this quantity r cosine squared theta plus r sine squared theta, we can factor out a value of r, where we know that cosine squared theta plus sine squared theta is equivalent to nothing more than just r times 1 in value. All right, cosine squared theta plus sine squared theta being equivalent to 1. So r times 1 is just the value of r. And the determinant we see here for this transformation matrix just becomes this value of r. All right. Now, what we're going to next do here is consider now this double integral over region R with respect to the area of R in terms of rectangular coordinates. We know that that double integral, right, over region R with respect to the area of R can consider the area of R, that change in area over region R, to be broken down into the change in x times the change in y, or become the change in y times the change in x, which represent an infinitesimally small area when multiplied together to give us dA, right? Being expressed in terms of these infinitesimally small values of x and y. And what dx dy correspond to is delta x and delta y in the limit of the Riemann sum. Where if we consider the Riemann sum in this case, we would note that the double integral over region R with respect to x and then with respect to y might be represented as this double Riemann sum seen here, right? Where what delta x represents is just the length of the ith subregion of R, and delta y is just the width of that ith subregion, such that when we take delta x times delta y, it gives us the area of the ith subregion of R, right? And what do we know about the ith subregion of R and how it would relate to the area of the ith subregion of P, right? Well, it would be just a scalar multiple of the ith subregion of R, right? So we set that up here this way. Now, from the linear transformation, we know if R of x comma y is the area of region R in terms of x and y, and r of r comma theta is the area of region R in terms of r comma theta, then what must be true is that the area of region R in terms of x and y must be just the determinant of t bar, that transformation matrix, the determinant of that transformation matrix times what would be the area of region R in terms of r and theta, right? Where since the area of region R here is represented by delta x times delta y, and letting the determinant of t bar sub I equal r sub I be the determinant for the linear transformation matrix for this ith subregion of R, and r of r comma theta, let that be equal to delta r times delta theta, will end up implying then that delta x times delta y, this area here, for this ith subregion of R, must be equal to the determinant of t bar over this ith subregion, which is represented by r sub I, right? R sub I, times what would be the area of region R in terms of r and theta, right? Which would be given by delta r times delta theta. So if we go back to this Riemann sum calculation and replace the delta x delta y with r sub I times delta r delta theta, we'll build this result. So that double integral over delta r, the double integral over region R with respect to the area of A, which equals this idea just the double integral over R with respect to x and then y in the rectangular context, equivalent to this Riemann summation, would be equal to then a similar result where delta x delta y gets replaced with r sub I times delta r delta theta. All right? Delta x delta y gets replaced with this quantity here, where returning with back to double integration with our understanding of the definite integral, right? This does return to the double integral over region R for what would be r dr d theta. And this value of r would incorporate itself into the integrand of this double integral. And the integral would happen very specifically with respect to the order dr d theta with the setup we have presented for region R in this case. Now, what the scalar multiple of R is known as, right? The scalar multiple of R found in the integrand of this double integral of R with respect to the area of A, written in terms of R and theta, these polar coordinates, it's known as the Jacobian multiplier for the transformation of the double integral in the rectangular context into this double integral in the polar context. And a similar result can be seen for the triple integral transformation that we have when we look at the triple integral over region D with respect to the volume of D, right? When converting from that rectangular context, dv, dy, dx, that Jacobian multiplier incorporates itself into that integrand due to the linear transformation or the approximate linear transformation we have going on between r and theta into x and y. All right. This supports the Jacobian for our polar transformed double integrals and for our cylindrical transformed triple integrals. All right. That value of r just comes from approximating our linear transformation matrix with these partials from the parameterization of x and y in terms of r and theta, and calculating the determinant of that transformation matrix. Right? That determinant of the transformation matrix is what yields this Jacobian multiplier known as the value of r. This is true for that double integral into polar functions and the transformation of the triple integral into cylindrical coordinates, right, and descriptions of space. Now, what we might consider then, lastly, is the Jacobian multiplier that we see in the spherical transformation. And where it comes from, right, where it comes from is, first of all, the understanding that in the transformation between x, y, and z and phi, rho, phi, and theta, x, y, and z relate to rho, phi, and theta with the following parameterization. Where, since we are transforming in three-dimensional space, the linear transformation matrix is going to be made up of a 3 by 3 matrix, where the rows of the matrix are going to be the partials of x, y, and z respectively with respect to the parameters rho, phi, and theta respectively. Right? Again, here I'm apparently going to have to fix all these quickly. Right? So we go through, it's going to be all these partials that are going to now make up this transformation matrix, where we can calculate these partials for the parameterization given above, right? And you can see that I do fill these partials in the right-hand side of this result. Right? This sine of theta, or sine of phi cosine theta, is just the partial of x with respect to rho. Right? Well, rho is only to the first power, so that leaves just behind the sine of phi cosine theta. Right? This is then the partial of x with respect to theta, phi, and this is the partial of x with respect to theta. We see similar partials with respect to y, or for y with respect to rho, phi, and theta, and similar partials for z with respect to rho, phi, and theta. Right? Where the Jacobian comes from the determinant of this calculation, right? The determinant of t bar. Now, if you remember how to calculate a determinant for a 3 by 3, it is the product of this component times the cross product of this with this minus this times that, right? That produces this first result, minus this component times the cross product of this with this times this, well, minus this times that, which gives us this result, plus this component times the cross product of this with this minus this with that, which produces this result. Where now if we take those three values seen in our cross product, this is a little bulky. I can bring this up, I think, without erasing too much. Yeah, well, that's about as high as I can get that. So we start to simplify that. What we will do is I group this term with this term. That becomes my first group. The second group comes from the second term grouped with this interior term. That becomes this group. Where within each of those groups, you'll notice here, I can factor out a rho squared sine cubed of phi from each of these terms, and that'll leave behind a cosine squared theta, sine squared theta being added together, which is equivalent to 1. And from this group, I can factor out a rho squared sine phi cosine squared phi from each of these groups, which will leave also behind a cosine squared phi, or theta, sine squared theta being added together, which will also equate to the value of 1. You see that happening here in this next step. Right? Yes. And then hold on. That step just looks repeated from the one above. So let's drop that one. This is the step we want to see happening. Whereas if we factor out those respective quantities, right, that will leave behind this value inside the group here, which is just the value of 1, and it'll leave behind this value inside this group here, which is also just equates to the value of 1. So it'll be this times 1 plus this times 1. We see that in the next stage here, where that then simplifies into just this plus this. Right? Where in those two terms, you will notice some common factors. Rho squared and one value of the sine phi. If you factor that from each term, you will be left with sine squared phi plus cosine squared phi in the group, and that equates to the value of 1. So in the end, we will break this down to a determinant value given by simply the rho squared sine phi value. Right? Again, going back implies that the determinant of this transformation matrix is just rho squared sine phi. Where what can this determinant be used to do is scale the volume seen in the description of R in terms of x, y, and z into the volume seen in the description of R in terms of rho, phi, and theta. Right? Multiplying rho, the change in rho, the change in phi, and the change in theta by this determinant will produce the volume in terms of region R expressed with respect to x, y, and z. And that's why this rho squared sine phi becomes known as the Jacobian multiplier, seen in the transformation of the rectangular description of region D into this spherical description of region D. You can see here that integrand incorporates itself in as a scalar multiple coming from this determinant of t bar being multiplied by this description of region D space, right, to obtain the description of region D space in terms of x, y, and z. Right? Now, folks, again, this is, a little off the beaten path. This is, however, is related to multiple integration. It is where we get this Jacobian multiplier from in these calculations. In terms of accountability, your accountability is minimal, but I did want to show you where that idea does develop from. And really, anytime you are doing a change of variables, whether it's in a triple integral, a double integral, or even in the case of a single integral calculation, you really are always performing in a sense, an approximation of what would be a linear transformation that's happening in an n-dimensional matrix system, right? In single derivatives, it's a one-dimensional system. In double or derivatives, it's a two-dimensional system, and in a double integral, single integral, and a triple integral, it is a three-dimensional transformation. Right? Again, it comes from linear transformations of R sub n and how that affects the variables change in those regions. All right? And all that brings about what we know as the Jacobian multipliers in all of our cases for change of variable. But with that said, folks, I will end that video there. I hope you're all doing well. I hope you're hanging in there. You have a couple more weeks until the end of the semester where You will, yeah, you got one more test after what you currently are working on, and then we do have the final exam, so make sure that you are keeping on top of your studies. With that said, I'll see you either in Collaborate or I'll talk to you in the next video. See y'all then. Later.